Okay, in this re-recording of the radio sources, we will actually just learn about the radio sources in the sky. So first, the most common type of radio sources are so-called hot gas. So hot gas, there are various places in the universe that actually has the hot gases, and then the resulting in the ionized particles, such as protons and helium nuclei and then electrons. And then when the free electrons actually occasionally encounter with other charged particles, they feel each other through the Coulomb force. So then they got accelerated, and based on the degree of this acceleration, the charged particle being accelerated need to actually radiate energy, so radiate photons. And when the acceleration is small, then they radiate in the radio frequency. So this is actually known as the free transition. And then say exactly the same physical mechanism that actually happening at the high acceleration part, which is actually the resulting in the radiated photons at the high frequency, such as like the X-ray. It is known as bremsstrahlung, the radiation. So when it is actually free transition, this type of the ionized particles are actually filling each other, getting accelerated, producing the emission. It is known as a free transition. One of the famous place that seeing this free transition is the Orion region. So Orion region is about 500 parsecs away. So that is give or take roughly about 1500 light years away from the Earth, and then that's the belt region of the Orion, and then that's the sword. Around the tip of the sword, there is the site of the massive star forming the regions, and then this region has like really large giant molecular cloud known as the Orion Nebula. And this Orion giant molecular cloud is the site of the star forming regions, ongoing star forming regions, currently creating like millions of stars. So when this region is seen in radio, we can see that actually that region is really glowing brightly in radio. The image is because of the lots of the ionized particles that actually interacting with each other, they producing lots of free transition and then radio emission. Another type is atomic and molecular transition. We know that actually that the electron transition actually has the adjacent energy level, and when that actually the energy difference is actually very small, they actually radiate at the radio frequency. One of the most important the radio transition is actually the produced by the hydrogen, and hydrogen is composed of protons and electrons. We know that actually these protons and electrons has a spin, and then it's a spin axis orientation actually cause two different energy levels with a very small energy difference. When this proton electron has the parallel spin axis, it has a slightly higher energy level than the opposite direction. And when this electron is untouched in the higher energy, then after some time they flip to the lower energy, radiating away the energy difference. That is the 1420 megahertz, the frequency in terms of wavelengths. That's the famous 21 centimeter hydrogen emission. So when the galaxy is actually full of hydrogen, and including our Milky Way, so when we see these normal spiral galaxies such as NGC 628, we see that actually concentration of hydrogen emission. Okay, so normally that actually the hydrogen is concentrated along the spiral arms. So when we see from the side view, these spiral arms are rotating at different the velocity. So meaning they're rotating at the angular speed, but because of the projection effect, each arms actually has a slightly different radial velocity component. Okay, And then this radial velocity component actually is causing, when we see from the side, we can see that actually the several arms has the different, the Doppler shifted hydrogen emission, the 21 centimeter emission lines. This is in fact actually the case of our Milky Way. So when we see various the regions along the galactic plane in our Milky Way galaxy, we see that actually various different the spiral arms by detecting the 21 centimeter the emission that actually coming from the concentrated neutral hydrogen in our Milky Way, the galaxy. But this particular the spiral galaxy NGC 628 is the face-on spiral galaxy. So that means actually there is no net the radial velocity shift due to the spiral arm. So that actually what we see is actually one combined strong 21 centimeter emission peaking at the about 1417 megahertz, and rest frequency is 1420. So that difference is due to the relative radial velocity difference between the Milky Way galaxy and the NGC 628. Okay? Another type of the radio sources are electrons interacting with magnetic field. In the universe, various places and various objects actually has magnetic field, like the stars has magnetic field, and interstellar medium has magnetic field, and even the galaxies has a magnetic field, and it is suspected that actually the intergalactic the regions may have also that actually some the magnetic field as well, although that actually can be weak. So that means actually the lots of the ionized particles that actually that occasionally encountering with this magnetic field, and then this normally that actually is a straight the ionized particle that actually the traveling straight line with the transitional velocity of v. When it encounters the magnetic field, it has the same translational velocity, but because of the Lorentzian the force that actually interacting with the magnetic field, it has the circular acceleration component. So again, that actually when the ionized particle is accelerated, they need to radiate energy, right? So the degree of interaction with the magnetic field, and also that actually depends on the speed of the incoming the ionized particles. Occasionally that actually frequently this encounter radiating energy in the radio the frequency. Okay, and then also that actually that one thing the notable about the synchrotron radiation is synchrotron radiation is highly polarized. So compared to the sunlight, for example, sunlight has unpolarized, meaning that actually that the oscillating frequency of the electric field or magnetic field, it doesn't have the prepared domain, so there is a mixture of many different waves that actually that has the oscillating electric field, the orientation in any random direction. But in synchrotron radiation, they produce really highly polarized the emission. So this synchrotron radiation is prevalent in astronomy, and next the few slides are actually showing the examples of those synchrotron radiation in radio frequency. First is the Jupiter. Jupiter seen in optical images. So this is the rotation axis, and Jupiter rotates really fast for this given size. So yet the rotation period is only a few hours. Okay, so because of this gas ball that they're really spinning really fast, its upper atmosphere is actually broken into the multiple the subzones. So that actually it has to make a long story short, that actually it has the multiple band. It's basically similar to the Earth's atmospheric circulation pattern broken onto the three major cells. Okay, so because of the faster the rotation of the Jupiter, it actually has many more the zones, And so that means actually this Jupiter's rotation axis is actually this pretty much vertical. When we observe Jupiter in radio, it has the concentration of bright radio emission as if that actually has the magnetic pole is actually tilted, so that's away from the rotation axis, and this magnetic polar regions has the concentration of magnetic field lines, so that actually there is the more intense the synchrotron radiation coming from the polar regions. Okay? And the tilted magnetic pole from the rotation axis is very common. In fact, actually our Earth also has the magnetic the axis is actually the offset from the spin axis, and every the few thousand years that actually this polarity of the magnetic field is actually somehow flipped for some unknown reason. Okay, so like in Jupiter, that actually we believe that actually the same thing, the similar thing is actually happening. So the magnetic pole is actually offset from the spin axis, and this the polar regions of the Jupiter has actually showing really concentrated, strong synchrotron radiation, and in radio. Similar things that actually can be seen on the surface of our sun. So when this sun is actually observed in optical, we see that actually photosphere, okay, and this bright filamentary structure called flage, and then also there actually this dark spot known as the sunspot. Sunspot is the region of the really highly concentrated magnetic field lines. So magnetic field lines somehow that actually prevent that convection, so that actually that really hot materials from the deeper center of the sun is actually just coming from, I think, they appearing from the surface, so that actually that less amount of energy is actually transported into the highly demagnetized regions, so that actually its regions is actually colder and then cooler than the surrounding medium by roughly about 2000 degrees. So they appear as a dark compared to the brighter, hotter the surrounding regions. So these sunspots are the cooler regions with really highly concentrated the magnetic field lines. So that means actually that the ionized particles actually accelerated along the concentrated magnetic field lines around the sunspot, so that actually these sunspots actually when they're seen in the radio frequency, they glow brightly in radio. So this is the another example of synchrotron radiation. Right? The example is the supernova remnant. Supernova remnant is accelerating the hot gases, so ionized particles, so that actually these the accelerated ionized particles actually interacting with the remnant of the magnetic field lines of the supernova progenitors of the supernova, the star, and then these actually that the magnetic field line interaction with the accelerating the expanding the ionized particles produce lots of the synchrotron radiation. So when this Cassiopeia A, which is the famous supernova remnant, is commonly known as known as Cas A. Okay? Cas A is seen in optical. It has some edge of the supernova remnant, the exploding, I think, expanding the edge of the supernova remnant actually visible and recognizable. But when it actually seen in the radio, we can see the fully enclosed expanding shell structure of the supernova remnant, because there are some the synchrotron radiation, which really the really very efficient process. Then another the really famous example of the synchrotron radiation is the pulsar. So when a star that is about the 2 to I think about 4 times the mass of the sun eventually evolved and then run out of the fuel at its core for the nuclear fusion, and actually eventually just they lose most of its outer the materials through nova. Okay. Then what is actually the left at the core is the really hot ashes of the nuclear fusion, the ash, typically helium and then maybe silicon, or the mostly the helium, the nuclei. Then this helium nuclei actually just they're feeling the self-gravity, but because there is no ongoing nuclear fusion at the core, there is no way to actually just really counteract its self-gravity. Normally, the actually normal star, the producing lots of energy through the nuclear fusion, that radiative the energy that actually can counteract and can actually just act against the self-gravity, so that actually it maintains the balance. But now that actually the remnant of nova doesn't have actually that nuclear fusion, so there is no the counter, the force that actually they're acting against the self-gravity. So they got actually squeezed all the way until that actually that degenerate pressure of the subatomic particles can actually can resist against the self-gravity. So that the degenerate pressure is coming from the neutrons. So all these ashes are actually squeezed into the small ball, typically about the size of the 10-kilometer diameter. That's about the size of Athens. And then these highly concentrated squeezed materials, now that actually, because actually it is originally that size of the star, they're actually squeezed into the small, the ball of the degenerate materials. They need to actually spin really fast, because the original star are actually spinning at some certain speed, but they're actually squeezed into the very small ball. Meaning that actually angular momentum conservation dictate that actually this small concentrated squeezed the neutron ball should be actually rotating really fast. So newly formed neutron stars are actually spinning really fast, about 1,000 times per second. And also that actually when they actually get squeezed, not only that actually angular momentum is actually dictating the spin is actually just increased, the magnetic field is also that actually just they collapsed together with the materials, so that actually that the magnetic field is greatly concentrated and really strong compared to this normal star. So meaning that actually that this the fast spinning the ball of neutron, sphere of neutron, has the typically tilted strong magnetic field. Then these polar regions are actually just spinning around this spin axis about 1,000 times per second. So around the polar regions, there is a strong concentration of synchrotron radiation, and if that actually the Earth is actually they happen to be actually in this direction, and we put our radio dishes in this direction, then we see that actually that really the fast pulse of the radio emission appearing in a really exact interval, and the pulse are actually separated by only a few milliseconds. So these are actually known as the pulsar. Okay, and pulsars are the end product of the massive stars evolution, and the pulsar is the prime example of synchrotron radiation at the radio frequency. So when we actually see the night sky in radio, we can see that actually there is the circular regions. These are typically the stellar remnant, not the supernova remnant. Okay, we can see few, and then these filamentary structures are typically indicating the star-forming regions. And there are lots of that actually the point source. Okay. And this point source look like a star, but the stars are actually at the radio frequency. They are too faint, and then they cannot be visible in this type of radio observation. So in fact, they're actually detecting the star's photosphere at wavelength, the radio frequency is extremely difficult. And all these point star-like objects in this radio sky are, in fact, it's far, far away, the galaxies and quasars. Okay, so the young galaxies, soon after the creation of the universe, they are actually building the stars actively, and they have lots of the hydrogens and whatnot, so that actually they produce they are bright in radio, so that actually that all these dots, the point source, the like object in seen in radio, are actually as the faraway young star-forming galaxies and quasars. Another example of the radio sources are the molecules. Currently, we know that actually more than 100 molecules actually discovered in the space. Okay, mostly coming from the comets and then whatnot, and then in the colder regions in our the solar system. Okay, and these actually molecules are like they contains lots of the amino acid and then sugar and then alcohol molecules. They can actually provide as the prebiotic molecules, so that for the environment, they can actually form into the some biomolecules that can result in some life in other places. Okay, and the molecules have multiple nuclei. Okay, so typically that these molecules are actually mainly they composed of hydrogen, carbon, nitrogen, and oxygen. So these are the CHON are the four major building blocks of the molecules in the universe. Okay, and these molecules, the nuclei, actually are filling each other in some way that occasionally depends on the excitation from the surrounding medium, whether it is the mechanical shakeup or like through the kinetic motions or radiations or the collision between them. Some they are actually excited in some way that actually says like the oxygen and then the carbon are actually just vibrating. So as if that actually you just hit some small spring that actually vibrate. This oxygen and then carbon atoms are actually just feeling the vibration. Okay, and then the carbon to carbon actually just feeling the vibration as well, but at the different frequency. And this double bond, this carbon and oxygen, actually had also at the frequency. Not only that, actually this vibration, this whole molecules can actually just do this spin in one direction of spin, or the other direction of spin has the slightly different the energy levels. So this typical seemingly that actually simple the molecules are made of the 2 carbons, 2 oxygen, and then 6 hydrogen can have the many, like sometimes actually the tens of thousands different energy levels because of the various possible vibrations and the rotation mode. So these energy level difference for the typical molecules, the vibration and rotation, are actually just visible in the radio, they're detectable in the radio frequency. So that's why that actually nearly all the discovered molecules in the sky so far, okay, so more than 100 are predominantly discovered in radio observation. And in fact, in the 70s and then 80s, there was the prime time, and then there was the international race that actually detect this additional new the molecules. Okay. And in fact, actually, one of the advisor during my postdoctoral research period, his name is Dr. Ben Zuckerman from UCLA, and he actually once discovered the collection of alcohol. It is the ethyl alcohol. So ethyl alcohol is the drinkable. The amount of the ethyl alcohol that the several times the mass of the sun. So that actually is the international the bar, right? And then there is actually endless the supply of alcohol. And another recent, I think, the noteworthy discovery in radio astronomy is the detecting the relic of the hydrogen cloud that actually once believed that actually this formed the ancient galaxies. So soon after the Big Bang explosion, we know that actually that the 92% of the materials in the universe are hydrogen, and roughly about 88% of them are helium. So that the galaxies actually must have formed, and then inside in the galaxies, the stars actually recycle some of these primordial the element, so they're actually creating the heavier the element gradually. Okay, so there must be some ancient hydrogen cloud left over from the initial galaxy formation, and then this type of actually the discovery of ancient the galaxy, the building block, can be actually the observable from the nearby galaxies to our Milky Way. So there has been some ongoing effort such as like this observing around the nearby the galaxies to the Milky Way, such as the Andromeda galaxy M31. So when the M31 was observed in the 21 centimeter wavelengths, that was actually seen in this nice spiral structure. So that's shown in this blue hue. And by observing, I think the single dish, it's called the Green Bank telescope. That's the largest steerable the radio telescope with the aperture size of 300 feet. This is actually a great telescope with great sensitivity to detect hydrogen cloud. Okay, so not from the 21 centimeter that the spin axis flip. This is actually the different way of actually detecting hydrogen cloud in some way. Okay, so that actually this Green Bank telescope that actually just looked around the Andromeda galaxy region and actually found the concentration of hydrogen blob, and the blob, the detection of blob so close to the M31 cannot be a coincidence. So we believe that actually these are the connected. So in some way that actually that if it is connected, then isolated large amount of hydrogen, the cloud away from the galactic plane, is actually unusual. So this may be a hint of the relic, the hydrogen cloud that actually they formed the galaxies in the beginning of the universe. Okay. When we look at the center of our Milky Way galaxy in radio, we can see that actually that there are lots of different structures, such as the supernova remnant, and then still there actually that the enclosed the circular structure of the supernova remnant, and then another supernova remnant as well. So that center of our Milky Way region is actually has a lot of really high activities. So that actually that the massive stars actually formed. And when these massive stars, they're of this maybe 10, 20 times the mass of the sun, formed, they usually explode as a supernova within 10 or 20 million years. Okay? So there are lots of the supernova remnant, and the hint, the indicating actually that lots of active formation of massive stars. Okay, and then also that actually we can see that actually some of these thread, or known as the filamentary structure, when the central region of our Milky Way is seen with the latest radio or the telescope, we can actually see the really spectacular details of the radio, the object in the Milky Way galaxy. We can see that actually the lots of the smaller supernova remnant, okay, and the really gory details of the filamentary structure. The nature of this filamentary structure is actually yet unknown, okay, and this is the region of our Milky Way galaxy. So the Milky Way galaxy is around here, okay, center. So that is the location of Sagittarius A, and then there is the large filamentary structure. So this is the home of the supermassive black holes at the center of our Milky Way, and these supermassive black holes actually basically just causing the rapid the evolution of the interstellar medium, so actually producing lots of stars and then very the strange structures or filamentary structures or not. So that actually these the galactic regions center the observed at the radio frequency actually provide, because the radiation doesn't actually that interact with the interstellar medium that well. So that means actually the galactic the central regions they observed in radio, we can actually see through the materials, any intervening materials, and then being able to actually see the really detailed structure of the center of the Milky Way galaxy. Okay? And during the video that actually describing the array interferometry operation of the radio dishes, I mentioned about the latest the deployment of the array of the telescope in the Chilean desert called Atacama Desert. Okay, so Atacama Desert is the 16,000 feet above the sea level and very dry. So that actually that is a very good place to operate the radio, the observatory, especially in the highest frequency domain. So ALMA is actually just has the several dozens of the large radio dishes that actually that operated in the array environment, right? And then actually working at the highest the frequency of radio or the wavelength range, so that actually it can provide the really high angular resolution the images. So this is actually that about a couple of about 2 arcsecond away, I think 2 arcsecond the size, and the in terms of physical scale, that's about a couple of times larger than our solar system. And then this is the true image of ALMA observation of HL Tau. HL Tau is a young star. It's about 1 million years old, and this is about 400 light years away from the sun. When these the young stars actually they observed in the radio, we expect that actually the many of these young stars surrounded by the forming planetary system called protoplanetary disk. One thing that actually really that surprised this image that actually that surprised many astronomers was actually that it is showing that actually the cavity, lots of concentric rings with the cavity, right? And this cavity is actually can be explained and then interpreted in such a way that actually that like in this artist illustration of the forming planetary systems, that if the planets, massive planets are formed, or forming planet that is actually situated in the middle of the planetary disk, they actually they accrete material from the surrounding around its orbit. So actually basically creating the cavity or the avoided region or the void regions. So that actually this hydrogen cloud and then are actually basically just used up, sucked up into this forming planet. So meaning that actually this HL Tau, this star is actually at the center. And then there actually we can see that actually several the massive planets are actually currently forming. So this is actually really spectacular, unexpected view of the protoplanetary disk that actually observed by ALMA. So far, that actually as we learned about that the many of the radio sources that actually in the night sky that can actually provide unique astrophysical information that cannot be obtainable at other the wavelength regions, unique to the radio astronomy.